Hello everybody, welcome back to Fastware. So today we will start with enjoying a little bit of whiskey. The best thing in the world. I'm sorry, I'm a little tired today. It's been 9 hours straight coding at my day job, but I need to prepare a video for you guys, so I'm gonna do my best. Please be patient with me if some things I might forget to say or something like that. Always remember to leave your questions or misunderstandings in the description. As you see, it's already happening. Yeah, so leave it in the comments below. I read them all and I'll try to answer anything that might be unclear or that maybe I didn't explain well enough. So, with this short introduction out of my way, now I'm gonna enjoy another sip of whiskey. And we will dive into our memory allocator implementation. So, a little recap what we've done last time. We have created an API. So what we have here is we have a mem block, we have a stack allocator create info where we can create an allocator, have a destroy, allocate, deallocate all, preferred size, and owns functions. We also implemented a little align t, kind of a structure where we have a enum for different types of alignment supported by the system. And we can give a size, an alignment, and that size will be then aligned to that alignment, providing a new size. Also, we want to be able to check if a pointer is aligned to the specific alignment. So we provided these utility functions there as well. We have implemented a create function, but we stopped right there. So if something is not clear why it was done a certain way, please go check that other video. So we'll continue today by implementing the create, align, storage, destroy, and hopefully for stack allocator, all the functions that we need. We'll answer the main question about stack allocators, and I will try to explain to the best of my ability why it is useful and where to use it. Okay? So let's start with implementing the create align storage. As usual, I'm just gonna zip through and we'll talk about what I've done after the implementation is finished. Here we go. Right. So I think that should do it for create aligned storage. Time to take a break from typing and enjoy a little whiskey as usual. So now, what do we have? So we prepare our sizes to start with. So we have aligned alloc size, aligned mem space size, and the total aligned size. So I think this is straightforward. And we do two different things depending if the parent exists or not. So if the parent exists, we just call the allocate with the parent, which will basically do a recursive call back to allocate. Well, maybe not recursive, but it will call allocate with that particular allocator that is the parent. The only thing that might be confusing here is this alignment mask and given the alignment. So the reason why we need to do this is because the parent allocator has its own alignment, and it might be smaller alignment requirement than our current alignment. Therefore, what I do is I add extra space minus 1 byte, so alignment minus 1 byte to the address space, knowing that when align will run, it cannot shift more than the alignment requirement. So the usable address space and usable size cannot shift more than if it's, for instance, if the alignment is 16 bytes, it cannot move more than 15. So therefore, in that case, I would add this 15 bytes extra, knowing that this move should be successful. These asserts are here specifically for debug mode when we're going to be writing our tests, as we will be doing a bit later. So you will be able to see how we test these sort of semantics, right? That's for that purpose alone. So normally you don't expect this thing to fail at all, right? Once you implement it, it should be fully deterministic, right? So then for if the parent does not exist, so we want to call malloc. So this is an aligned malloc, basically. You can look up the POSIX headers. It's also part of C++ standard as well. So aligned alloc is now there as well. So given the alignment and the size, it basically allocates that many bytes aligned to the specific alignment that you require, right? So obviously in case 2, this should do nothing. It should basically be just returning exactly the same data back to us. Right. And then we just prepare some space for this align, we do our thing, and then we can return our data. So this is pretty much it for this thing. So this is how we would create the aligned storage. Now let's move on and quickly implement destroy. Since now we have this aligned alloc, it's a counterpart for the destroy, so we can basically be sure that the memory is released appropriately. So let's not leave it for later. Let's do it now. So let's crack on. Right, I think we're done with this for now. Obviously, we add many more cases when we will have them. So we have allocator type E stack. And of course, if it has a parent or if it doesn't have a parent, it does two different things. I think that's pretty straightforward. The only thing that might be confusing here is the reinterpret cast. Obviously, we're casting the allocator t into that. Now, the only question might be, why is this valid? Why we can do this? Is that not violating some sort of a type safety? In a matter of speaking, it does, but we can be guaranteed that it will work. The reason why we can be guaranteed that it will work is quite simple. So we always place the allocator type E as a first member, so where the this points to. So this is member at 0 offset. So therefore, casting the allocator type T directly to this type will pick up this particular value from it, right? So we need to be obviously cautious and careful when we implement other allocator types that we do exactly the same thing, that the very first thing there is the type. Otherwise, you will be reinterpreting garbage and then making decisions based on them, which obviously will cause problems. But as it is now, I think that's pretty good at the moment. Right, so what we will do is now maybe quickly run through and implement allocate, deallocate all, and then preferred size and ounce. So allocate is and deallocate are the two for stack allocator that are a little, so deallocate is very weird, and that's why you clicked on the video to understand why deallocate for stack allocator is weird, right? Allocate is more straightforward. Deallocate all is very simple as well. And I will show you all of these in a second. So let's get to work. Right, so what I just did is obviously very simple, just populated all the different types. So we just switch across every single case. We return when we need to return. So we'll be implementing these internal dialog for each different type of allocators, and we'll have literally symmetrical code and following through. So we will not implement directly here. Since all the code will be placed directly into this single CPP file, everything's going to be available to the compiler, so it can probably inline most of it, if not all of it, if you're not going to use too many switch cases, but yeah. And of course, we do have the case where if we have too many switch cases, remember from my evil go-to video, if you haven't watched that, please go watch it. If we have too many switch cases, the compiler generates pretty terrible code. What we can do is actually do better by just implementing a jump table, a const expert jump table that we can actually jump to the correct function directly. So that's all possible to do, and we will see if that's necessary, if we will need to squeeze another 2 or 3 cycles out of every allocation. But for now, it's good enough. Right, so let's jump in and implement internal alloc, deallocate all, and all of these. So I'll go through all of them, and then we'll talk about them. Okay? Let's get to work. A little whiskey before we start. Here we go. Right, here we go. I think we're finished with this. You're a good friend, my dear comrades, right? Anyway, enough kidding and joking. So, internal alloc that we have implemented, I think it's pretty straightforward. We align the requested size, we take the current available start of available memory space. We adjust it by the align size to check where is going to be its end. Then we compare that adjusted head if it's not reached over the end of memory space. So this is basically a boundary check saying, okay, so that size of allocation cannot fit in this, right? So imagine it can be even happening on completely fresh allocator. So you have 1 megabyte, you requested 2 megabytes. So it says, okay, so my memory space is from this address to this address. I align my thing, I align my requested size, which is 2 megabytes. And then I take the current head and advance it by 2 megabytes. That pointer is definitely going to be much further than the end of memory address for that allocator, right? So super simple. And here the allocator block start is now the new head if everything completed successfully. And then we return the previous head with the aligned size as a usable memory space for that particular allocation. So I think that should be clear, right? Now, next is the alloc, and the main question, why is it like that? So imagine, because the stack is basically a push pop, right? So your dealloc is your pop. You cannot pop from the middle of the stack, and therefore you cannot deallocate from the middle of a stack exactly the same way. We can deallocate only in the case where it was the last allocation that allocated this block that we're now deallocating. So very quick allocate, deallocate for something, right? So this is what's happening here. The adjusted head is basically we take this advanced pointer. Remember, we are advancing it. Now, if we take this advanced pointer and this is now a line size from a previous thing. So take that block start minus that size that was returned to us. It should put us back into the current head. So this is what that should represent. And now we're checking, basically, if that pointer that was returned is equal to that current head, because that's what was returned, right? So that's the PTR. So the adjusted head equal to that pointer. And if it is, then we say we reset the block start to the adjusted head. So we basically push our pointer back by popping the element off, or deallocating, so to speak. So deallocate all is trivial. Obviously, we just say block start is equal to memory space start. Internal preferred size, we just align it. Very, very simple. And then internal ounce, it's a range check. We're saying that if the block pointer is greater or equal to the beginning of memory space for the allocator and less than the end of memory space, because it cannot be equal to memory space for a simple reason, because if you're allocated on the boundary, you have 0 bytes, right? Because the end memory, so mem space end, sorry, is mem space start plus full size of it. So at least 1 byte and you'll have an overflow. So it needs to be less than that. And that's about it. So this is a simple range check. It could be improved by basically worrying about, okay, so memory space minus the end must be less or equal. So there's things that we can do to be more precise here. But most of the time it's usually not necessary. So therefore we're not gonna waste space and time. And what we're gonna do is we're gonna do a single ampersand here, not a double ampersand. Since we can allow both of these checks to happen at once, it's so this is the binary and so the double ampersand and forces to first expression to be evaluated, then a second expression to be evaluated, while the binary can allow both to be evaluated at once, right? So very, very simple. Obviously compilers optimize most of these, but it doesn't hurt. Right? We are good programmers. We understand what's happening here. So next time, I think what we will do is start by implementing some unit tests and some performance tests to compare, to see how our allocator basically performs compared to malloc and new, and the unit tests for correctness checks. Anyhow, I hope you liked this video. If you did, please leave that like. It really, really helps. Leave your comments, questions. I really enjoy reading when people have something to say. It's great to engage with you guys and talk about these sort of things. Maybe I made mistakes, correct me. Look at the source, it's available on GitHub repository, the link to which is in the description below. And of course, subscribe if you haven't. It helps me and my channel and boosts my ego as usual. Right, so thank you so much for watching and have fun writing fast code. Thanks, bye.